Hey everybody, this is Mr. Beckstrom, and today we're going to take a look at section 3.1, and here we're actually going to introduce the idea and definition of the derivative using all of this limit information and rules that we have discovered and found so far in chapter 2. So let's first of all kind of remind ourselves the average rate of change on some interval. Remember, we're looking at the slope of the 2 points from the secant line. So we already know how to do that. To find the slope of the secant line, you're really just taking the y2 minus y1 over x2 minus x1, where f of x is your y2, f of a is your y1, here's your x2, and that would be your x1 in that case. So we look to see as one of the points gets closer and closer to the other points, one of the x values gets closer and closer to the other x value, we can actually then estimate or take a good guess at what the slope of the tangent line is at that point. So we can really use the definition of limits here to come up with a limit that solves for the slope of the tangent line at any point on a curve. And here's the one that we're going to use right here. So the m sub tan, which is the slope of the tangent line, is equal to the limit as x approaches a. That means those two x values are getting closer and closer together. And we're using the same formula as before here. This is where we're looking at the slope of the secant line until it becomes the slope of the tangent line. And if we were asked to find the formula for the line for that tangent line, here it is right here. This is using the points a, f of a, and that slope of the tangent line that we found, and this is in point slope form here. So let's go ahead and use this instantaneous rate of change formula to look at an example here. So let me go ahead and put that in. So here from the exercises I have f of x is equal to 1 over x, and we want to look at the point -1, -1. Now sometimes they give you the entire point, and sometimes they're just going to give you the x value. If they only give you the x value, you can just plug it into the function to get your y value. Notice if you plug -1 down here, and for x, 1 over -1 is just -1, so that's your y as well. So let's kind of first pull up my calculator and see if we can kind of at least get an idea of what that slope is going to look like. So if I go to my y equals, and we're going to put that function in here, 1 divided by x. And then let's go ahead and trace that. Here it is right there. And if I hit the trace button and make sure I'm on the wrong one. Moving over from? Let me try this way. There we go. All right. And if I get this x close to -1 there, so it's going to be somewhere, oh, I'm still using my window from before. Let me go back to zoom, and we'll do a standard zoom. I don't know if that helps that much, but once again, trace, and we'll try to get real close to that -1. And of course, the y is -1. We already know that. But if I'm looking at that slope of the line there, it's going to be going from upper left to lower right. So I should get a negative value for the slope. And it doesn't look like it's that steep. So I'm guessing I'm going to get some value that's going to be less than -1. But we'll see when we put it in the formula here. So go ahead and see if you can solve this. Just kind of take this information here, put it into the slope of the tangent form formula, give it a try, see how far you can get, and then we'll go through the solution. All right, so what we're going to do here is we're going to set this up in the definition here. So this is m, the slope of the tangent line, is equal to the limit as x approaches, in our case, -1. And then we're going to put everything up here. So the function is 1 over x minus f of a, that's going to be f of, here's my a, -1. So if you plug a -1 in there, 1 over -1 is -1. So this is going to be minus -1 all over x minus -1. So this here is what we're talking about. Now for each one of these lines, I'm going to keep the limit there. I'm just going to write a little quotation marks because I don't feel like rewriting that. But basically what we're going to try to do is we're going to simplify this. The reason being is because if I stick the -1 in there now, I'm going to end up getting 0 over 0, right? Because this is going to be 1 over -1, which is -1, plus 1 is 0, and then we have -1 plus 1, which is also going to be 0. So if you plug the -1 in here, you get 0 over 0, which is the indeterminate form. And that means that we need to keep going and try to cancel something out here. So let's go ahead and try to see if we can simplify this. So I'm going to combine the top there. So this is going to be 1 over x plus, and I can change 1 to x over x. So I have a common denominator there, all over x plus 1, and then copy the limit there again, and if I add those, I'm going to have 1 plus x over x all divided by x plus 1, and then if I multiply by the reciprocal of the denominator, that is going to be the limit there of x approaches -1 of, and I'm just going to end up getting 1 over x because we're multiplying by the reciprocal of that, and it'll cancel out. Therefore, now I can try to put that -1 back in there. So 1 over -1 is equal to -1. So that is the slope. That's the slope of the tangent line at this point for this function here. I thought it would be a little bit less than -1, but I was wrong. Sometimes it's a little tricky looking at that graph. That's my slope, and then what I can do if I want to find the form, that would be y minus f of a, which we said was -1, is equal to our m, -1 times x minus this x value, which is -1. And then you can just simplify from there to get your equation. All right, let's look at another definition of the derivative using limits. All right, so the other formula that we use, so here's one, and now we're defining this as the derivative at a. We can also use this formula, and this is the one that I'm actually used to using more, and I think it's the one that you'll see more common when we're trying to find the derivative or the slope of the tangent line at a certain point. And this is as h approaches 0, h is going to be the distance between a and the x. So that means that the distance is getting smaller and those points are getting closer and closer together. And then we're going to have f of a plus h minus f of a all over h. And this is going to start off just like the y2 minus y1 over x2 minus x1, except we're going to be able to cancel out the a's on the bottom and just get the h. So using this formula, let's try to solve another derivative problem, this time using this one. Okay, so this next one is f of x is equal to the square root of x plus 3, and we want to find the derivative at the point 1, 2. Now remember, sometimes they don't give us the y value there, and if they don't, then we just plug the 1 in, and 1 plus 3 is 4, and the square root of 4 is 2. So that's how they get the 2 there. So go ahead, try this one using this second definition here, and then we'll go over it together. All right, so for this one, I'm going to need a little bit more room here. And once again, we're going to start off with the limit as h approaches 0 of f of a plus h. So what does that mean? It means we go to our function here and we replace x with a plus h. So this would be, replace the x with a plus h, so a plus h plus 3. That's our f of a plus h minus f of a. F of a means we go to our function here and replace x with a. So a plus 3 all over, Lori, all over h. And so we'll put the h down there. Now, if we were to go ahead and plug the 0 in, which we really should be checking right away, we're going to end up getting the square root of 3 minus the square root, excuse me, the square root of a plus 3 minus the square root of a plus 3, which is 0 on top. And then if we replace h with 0 on the bottom, we get 0. So we're going to get 0 over 0, which once again is that indeterminate form, which means that we need to work on this a little bit. So let's go ahead and see what we can do to simplify it. And one trick that you need to know, you need to have in your toolbox for these, is that when we see radicals with a plus or minus either on the top or the bottom, we need to think about multiplying that by the conjugate. And I'm going to show you how to do that. So first of all, this is going to, let me go ahead, actually, let's do it like this. So the conjugate is just the first term, and then you change the sign in the middle, and then the last term. So this on top is this minus this, so the conjugate would be this plus this. So I'm going to multiply both the top and the bottom by that conjugate. Let's see what happens here. So I'm going to do a plus h plus 3, and then plus, because that's the conjugate, a plus 3, all over, and then the same thing here, a plus h plus 3 plus a plus 3, a plus 3. And when I do that, the top becomes a difference of squares. That's why we are using the conjugate here. So it's going to be the first thing squared minus the second thing squared. So the first thing squared is just going to end up giving us a plus h plus 3 minus, and then the second thing squared is just going to give us a plus 3. Don't forget to put the parentheses around it because we're going to have to distribute that minus sign all over h times that big mess there. And I'm just going to leave it like this, times square root of a plus h plus 3 plus square root of a plus 3. All right, so let's see what happens here. So the a's are going to cancel out here because that's a plus a and a minus a. This is going to be a plus 3, and once we distribute this negative, that's going to be a minus 3, so those will cancel out. So all I have left on the top is an h, and I have an h factor on the bottom as well. So both of those will cancel out as well. So what I'm going to be left with is just a 1 on the top, and on the bottom will be this thing here. So that's square root of a plus h plus 3 plus the square root of a plus 3. Now, I want you to notice one thing, because I don't think I really explained this yet, but in the prior example, I went ahead and put the value in for a in here. This time I'm just leaving it as an a. And if I just leave it as an a, then that's going to end up giving me the definition for the derivative for any value of a that I have. So right now, if I were to go ahead and put the 0 in there for h, I'm going to end up getting 1 over That's going to be a plus 3 plus a plus 3, so that'll be 2 times a plus 3. Because there's 2 of those now. Remember, I'm putting a 0 in there for h. Once I apply the 0, I don't need to put the limit there anymore. And this is going to be the formula for the slope of the tangent line there. And then with my a there, I'm going to end up getting 1. So that'll be 1 over 2 times 2, which is 4. So that'll be 1/4. So that will be my, m tangent is equal to the, remember that's just the derivative at a, which is equal to 1/4 in our case here. Now if we put a different x value in or a value in there, then we would get a different slope. All right, let's move on here. So let's take everything that we've learned here and see if we can come up with the equation of the tangent line at this a value 5 for this function here, 1 over x plus 5. All right, so I'm going to go ahead and use the second definition. Like I said, that's the one that I use more often, but you can use either one that you'd like. But this says that you can pause it here and give it a try, and then unpause it when you're ready to go through the answer. But this says here that the slope of the tangent line is equal to the limit as h approaches 0 of f of x plus h. So this is going to be kind of a crazy one here, but this is going to be 1 over, we're going to replace that x with a plus h plus 5 minus 1 over f of a, which is just going to be a plus 5, all over, and then we're just going to have an h on the bottom here. So what's going to happen when we plug the 0 in there? We're going to end up getting a 0 on the top and a 0 on the bottom. So that means that we need to keep on going. So go ahead and try it from here and see how you do. All right, so this is going to take a bit of work here, but we can get this. So just like we did before, the first thing I'm going to do is I'm going to try to combine these two fractions here. So remember, if I have one denominator that's a and one that's b, then I always know that there's a common denominator of a times b, of ab. Just like if you had 6 and 5 as your two denominators, you can get a common denominator by multiplying those two denominators together to get 30. So I'm going to do the same kind of thing here. So I'm going to multiply the top and the bottom by this denominator here. So this is going to end up being a plus 5 all over, and this is going to be a plus h plus 5 times a plus 5. So what I did there was I just multiplied the top and the bottom by this denominator here, and then minus, do the same thing here with this denominator, so we get that common denominator. So you're going to get over here a plus h plus 5 all over a plus h, excuse my a, let me fix that a little bit there, a plus h plus 5 times a plus 5 all over h. Whew. All right, now that we have a common denominator here, let me go ahead and give myself a little bit more room. I can combine those, so this is going to be the limit as h approaches 0 of, and on the top here I'm going to get a plus 5, and then remember I have to distribute that negative sign among all those. That's going to be minus a minus h minus 5 all over that big thing, a plus h plus 5 times a plus 5. And then this is all going to be over h. Now notice that on the top here, the a's will cancel out and the 5's will cancel out, and I'm just left with a negative h. So if I basically multiply by the reciprocal of the denominator, multiply this fraction here by 1 over h, the h's are going to cancel out, and this is just going to leave me with the limit as h approaches 0 of, and we still have the negative there, and it's going to be 1 over this crazy thing here. A plus h plus 5, all times a plus 5. All right. So now I try to plug the 0 in again once I get that h out of the denominator by itself. And that's going to give me negative 1 over, and this is going to be a plus 5 times a plus 5. So this is a plus 5 quantity squared. And that's your formula for the derivative of the tangent line. And then to find the slope, we're just going to plug in that a equals 5 there. So this is going to be negative, let me see, 5 plus 5 is 10. 10 squared is 100. So my slope then, is just going to be negative 1 over 100. All right, so we need to remember that the original equation was, pencil here, f of x is equal to 1 over x plus 5 plus 5. Therefore, if we plug in the value of a, which is 5, we're going to get the point 5, 1 over 5 plus 5, which is 10. 1, 10. So this is the point on the curve that we're actually finding the tangent line for. So now we have a point and we have a slope that lends itself very nicely to the point slope formula. So that's how we'll finish this up here. So y minus y1, which is 1/10, is going to be equal to m, which is negative 1 over 100, times x minus x1, which is 5 here, which is 5. And you can either leave it like that, or if it asks for the y-intercept or slope-intercept form, then we're just going to distribute and then solve for y. All right, guys, if you have any questions, let me know, and I hope you have a great rest of your week. Thanks.